guys can see my screen, but do you see static on the sides, like anything like blurry on the sides, or is it like all
You're good.
panned out?
You're good. I think
It's
we can
not
start.
blurry, but there's a gray screen on the right side.
Okay, that's good. So we're having some problems. So I think everyone else can hear me, Anirudh, so try rejoining. So wait, everyone can hear me, I believe.
He can't hear you,
Yeah.
so if you're
Yeah, we can hear you.
Oh,
I can hear him. I can hear you.
Okay,
So can
so yeah, Anirudh, just rejoin. So to do this problem, we've done a version of this problem quite some times, but we're going to generalize it here. And so the trick is we want to find the sum of the interior angles of this polygon, and this is a pentagon. So what we're going to do, like our intuition behind solving this problem is we don't know how to solve, like we don't know how to really deal with angles besides triangles. Right? This is on polygon angles. And before this, we've only learned about triangle. We've only learned. Okay, I'm going to try to get closer to my mic. So we've only learned about triangles before, so it's a good idea to try to get triangles out of here. And a good way to do that is to draw some line segments, right? So here you see we've drawn two line segments, and since this is a pentagon, well, if you look at just this diagram, you can see three triangles, and the sum of the interior angles of these triangles must be equal to the sum of the interior angles of the whole pentagon. And as such, we have three triangles, and each triangle has a degree measure of, well, the sum of the interior angles of the triangle is 180, so 3 times 180 will give us 540. But this technique isn't unique to just pentagons. Like you can do, like, I think that's pretty obvious. Like if you have any n-gon shape, you can do a similar thing. And that's what we're going to generalize in the next problem. So using the same technique above, I want you guys to go ahead and do example 2.2. And Anirudh, you didn't really skip anything, so this is basically the first example. We've probably done this before, so don't worry about it. So go ahead and try to generalize this technique above to n sides. I'm going to give you guys about 2 to 3 minutes to do that.
So I believe I turned on private chatting to all people, so you can now private chat either me or Sahil.
Okay, so do you guys need more time?
yeah.
Okay, I'm gonna go ahead and go over the solution. It's pretty similar to above, but okay, so basically the intuition is if you have, let's just look at this pentagon and we'll try to generalize from this. So from this, let's say we focus on a vertex A, and you'll see this technique of focusing on a vertex is actually very powerful. And we'll see that in the following sections of the handout. But let's just look at vertex A. And in order to like get a diagonal, we know we cannot choose vertex A, vertex B, or vertex E, right? And that's because you can't choose like things right next to like a vertex. By definition, a diagonal cannot go to an adjacent vertex, and it obviously has to go to
Excuse
itself.
me.
And
I think
because of that, we have 5 minus 3 choices for the other side of the diagonal. So you see this is AD and AC. So we have 2 choices for this diagonal. And the first diagonal you draw, which is this, it creates a 1 triangle, right? It creates EAD. And then when you draw this second diagonal, which also happens to be the last one, the last diagonal you draw actually creates 2 triangles. So basically, let's say we have an n-gon, right? N-gon, from a given vertex, you can only draw n minus 3 diagonals. But every single one of these n minus 3 diagonals create 1 triangle except the last one. This means you have n minus 2 triangles we can create with the diagonals, and well, since these are triangles, their interior angles add up to 180, and thus the amount of the sum of the interior angles is therefore n minus 2 times 180. And as such, if you have a regular polygon and a regular polygon just has equal angles and equal sides, the sum a given interior angle will have a degree measure of 180 times n minus 2 over n, and this is just dividing the total sum divided by n. So we're gonna have a little bit more a tougher problem here. So a good idea would just to look at this formula. So go ahead and give 2.4 a shot. So wait, do you guys not understand the proof that I did?
The
Because it seems
solution
like
is the proof.
Woody and Krishna are asking. Wait, does everyone understand the proof above?
Yes.
In the meantime, go ahead and give 2.4 a shot.
We can probably give like another minute.
Okay, so I'm going to give you guys a solution. If you guys aren't getting it, maybe I would recommend you guys just to look at this formula, right? And so let's just read the question really quick. Given Claire adds the interior angles of a convex polygon and has a sum of 2017 after she does that. And then we're given that she forgets one angle, and we're trying to find the degree measure of that angle that she forgot. So if you just look at the formula we wrote right here, you can see that the sum of the interior angles must be a multiple of 180, right? It's 180 times some other thing, so it must be a multiple of 180. And what this means is that if we add the missing angle, we must get a multiple of 180. So if you look at 2017, and if you just do some mental math, let me just, so the nearest multiple to 2017 is, let me just, the nearest multiples to 2017 that are a multiple of 180 are 2160 and 2340, right? These are the ones that are higher than it. Obviously, it has to be higher than it because she forgot one angle. So these are the. So if you just look at these two angles, you see that if the sum of the interior angles is 2160, she forgot an angle of 143, and then you have like infinite many multiples after this that are also multiple 180. But if you just look at the next one, this corresponds to her skipping an angle of 323, right? And since this is a convex polygon, you cannot have something that is greater than 180 degrees. And obviously all the multiples after this are greater than 323. So all these ones that are 2340 and after are invalid. So the sum of the interior angles must be 2160, and thus she must have forgotten the angle of 143. So our answer is C. So if you were focusing too much on like just a single angle, you're not going to get anywhere. So it's a good idea just to take oh my stomach, just to take a bird's eye view and look at everything. So now we're going to go on to exterior angles, and I want you guys to try to use what you already know about interior angles and supplementary angles to go ahead and find this. Go ahead and try example 2.6.
By the way, this question is asking for the sum of the exterior angles. And I could mark some of those for you. Would that be like the angles outside the polygon, where those lines are? That'd be things like this one, this angle right there, and this angle right here, as well as all these angles. So what's the sum of those angles over there? And as you can see by the lines, one of the hints is that the interior and exterior angles, you're going to add to 180.
So the first thing we should realize is that it's quite hard to look at just directly find the exterior angles. If you just look at this problem, you can see that the angles are rather arbitrary. Like we can't find a specific angle. And because of this, we should look at we should look at something we do know how to find and then subtract some stuff. So basically what I'm trying to say is if you look at a given angle, let's look at this angle. You know, a given angle like this is made out of an interior angle and an exterior angle. But the thing is, we can find the amount of interior angle. We can, like, if I label all of these, we can find the interior angle component of all of these. So just doing some math. So we already learned from our formula above that if this is a hexagon, that the sum of the interior angles is given by, oh, what is this? Okay, ignore that. 4 times 180. Oh, I'm high. Okay, this is okay. So okay, forget what I just said. You can, if you extend all these lines, you're given 6 angles that add up to 180. And when we do this, we realize that for each given like straight angle, part of it is an interior angle and part of it is an exterior angle. So if you can find the sum of all these straight angles and subtract the sum of the interior angles, we'll get the sum of the exterior angles. And so we know if we extend all these sides, the sum of all the angles is equal to the interior angles and the exterior angles is equal to 180, 1080. However, we know from our formula above that the sum of the interior angles is given by 180 times 6 minus 2, or 4. And if you just multiply this out, this gives you 720, right? So we know that the sum, like this component of the interior of the straight angle, all of these add up to 720. So this means that the other component of the straight angle must be the exterior angle. And if you subtract these, you get 360. So the remaining part of all these straight angles will give you an exterior angle. So if you just sum up all of these, you get 360 degrees. So basically our game plan is to find the whole angle and subtract the interior angle. That's going to give you the exterior angle. And you see that 360, like if you repeat this process with all other angles, I mean with all other shapes that are hexagon or septagon or whatever, you keep on going up or down, this is not unique to hexagon. And you guys will get a chance to prove this in the exercises. So exterior angles always exterior angles of the polygon always add up to 360. And keep this in mind for the rest of this handout, because you're going to see that there's much faster ways to solve problems using exterior angles rather than exterior angles. And example 2.8 is an example of that. So go ahead and give example 2.8 a try. Okay, so does anyone need more time for this problem? Okay, it seems like no one's replying, so I'll just take that as we can move on. So if we're given the number of, we're trying to find the number of sides in a polygon where each interior angle adds up to 172 degrees. There are 2 ways you can do this. Now, if you try to do an interior angle approach, well, you can essentially, well, you know that since every angle is equal to 172 degrees, the sum of all the angles must be 172 times n, right? But we also know that from our previous formula, the sum of all the angles in a polygon is 180 times n minus 2. And therefore, you have an equation with n, and you can solve for n, and you can get n equals 45. But if you're lazy like me, you don't want to do all of this nonsense, right? So an easy way to do this is to just realize that, you know, the exterior angle of this angle 172 must be 8 degrees, right? Because 180 minus 172 is equal to 8. And we also know that the sum of the exterior angles in a polygon is 360. So therefore, you must have 360 divided by 8, which is 45 sides. And as you see here, an exterior angles approach is really fast, and we'll see more examples of this in the following pieces of the following problems. But here, we finally have a problem that doesn't only involve angles. You need to actually use, perhaps parallel lines, hint, to solve this problem. So go ahead and give example 2.9 a shot. Okay, I'm going to go ahead and start on the solution. So we're given that we have a regular 15 Polygon, and we're trying to find ACB, ACD, and ADE. And a good start to solve this problem is to just figure out what a single angle is, right? So one of these interior angles. And an easy way you can do that is, well, just using our formula for an interior angle, we know that the sum of all the interior angles must be 13 times 180. So one of the interior angles must be this, 13 times 180 divided by 15. And this will just give you 12 times 13. So every interior angle must add up to 156. So if you just label B, this must be 156. But we also know that this is a regular polygon. So AB is equal to BC, and all the sides are also equal. So this is an isosceles triangle. So 180 minus 156 will give us angle BAC plus BCA. So the sum of these angles must be equal to 180 minus 56, which is 24. And since this is isosceles, these are equal, so this must be 12. And just to see, someone asked me, where do you get the 12 from over here? And that's just because 180 divided by 15 is 12. So we now know that we figured out the first question. So angle ACB is 12 degrees. Now, if you look at the next angle we're trying to find is angle ACD. Well, we already know that this interior angle must be equal to 156. So 156 minus 12 is equal to 144. And boom, we're done with the second one. But how about the third one? Well, a good idea would just to find this angle and then subtract this angle, because we are looking for ADE, which is this angle right here. So let's just try to find ABC. And if you just keep on trying and approach with angles, you're not going to get very far. And one thing you could just tell by looking at this diagram, but we're going to prove, is that ABCD is a trapezoid. And once you realize that, the last part of this problem becomes pretty easy. So basically what I'm doing is I take this trapezoid and I flip it over. So like this is the trapezoid of ABCD. And it's not drawn to scale, but imagine it is. So let me just get my annotate tool. So we already figured out that this angle is 12 degrees. Because this is isosceles, right? And if you use the same method, you find that this is also 12 degrees, because you can use the same method on BCD. And now we can use some SAS rules. So basically, if we look at triangle ABD and CAD, you'll realize that they share both this side. Oh. Oh, okay. Okay, yeah. So one way to realize this is a trapezoid is if you just look at ABC and BCD, well, the ABC and BCD are congruent triangles, right? So that means the corresponding sides are congruent. So if I look at this side right here, AQC, this is congruent to BQD. And if we look at ABD and ACD, we'll see that these triangles are also congruent because they both share this blue thing, blue diagonal, and they also share this side. But that's just SS, right? Because we're given that they share the side BC. Oh, my bad. Just to make sure, I'm trying to compare ABD and CAD. So we know they share this side over here, and oh, okay, I get it now. So basically, a quick way to forget what I just said. Okay, let me just draw this again. So this angle is 12 degrees, and this angle is 12 degrees, and therefore this must be isosceles, right? So we know BQ is equal to QC, but I also know that oh yeah. So if I look at triangle ABC and BCD, this side right here, well, those triangles are congruent because they share this angle, and they also have the same sides right here. So ABC is congruent to BCD, and we also know that therefore um, AQC and BQD have the same length because that's the corresponding sides of ABC and BCD. So we already know that these lengths are equal, right? So these lengths are equal. That means that this length and this length has to be equal because if BQ is equal to A, then and the whole it should make sense. Like you have one tick mark and you have two tick marks, and this has one tick mark. This also must be the same length, right? Because this length is equal to this length. So these are also the same. And now if you just, do some math, you find that this angle is 156, and this angle is 156. So what that means is that this angle must be 12, and this angle must be 12, because this is an isosceles triangle. So that means that you have set parallel lines here. Sorry if that was a bit unorganized. I think I messed up some of my. I'll have to clean up the solution later. But basically, we've proved that this trapezoid, well, these two sets of lines are parallel. And once we've done this, we're basically done. Because we know that this angle right here, BCD, is equal to 156. And therefore, this must be equal to 180 minus 156, which is 24 degrees. Right? And now we're just trying to find ADE. Well, we know that this whole thing was added to 156. So our answer is 156 minus 24. That's equal to 132. So for the sake of time, I'm going to skip this problem and I'm going to go on to diagonals. But this is pretty much just another application of exterior angles. But I'll leave you guys to do that later. Okay, I want you guys to give you just a few minutes to try to do 3.2. Do you guys need more time on this problem?
No.
No.
Okay, for the sake of time, I'm going to start going over this problem. So we're given a polygon and let S be the sum of the interior angles of the polygon, and we're given that the interior angle is 7.5 times the exterior angle at the same vertex. So if you just break out some algebra, right? So 7.5 is just 15/2, and well, first let me specify that the exterior angle, let it be x, right? So we know x is 15/2, x is equal to 180 because an interior angle and exterior angle is just a straight angle. If you solve for this, you get x is equal to 360/17. So we now know the exterior angle. And what you could do after this is you could set up a formula using the interior angles, but who likes doing that? There's a really easy way of doing exterior angles. And the reasoning goes as follows. So we know that since every single interior angle is 7.5 times its exterior angle, we know every exterior angle is the same, right? That's pretty obvious. Every exterior angle have the same angle measure. And we also know that in a polygon, the sum of the exterior angles must be equal to 360, right? So x times something must be equal to 360. And you could just see by this fraction, it has to be 17. There has to be 17 sides in order for the exterior angles to add up to 360. So now we know that the polygon must have 17 sides. So now you can just break out a formula again. The sum of the interior angles must be 15, which is 17 minus 2 times 180. So we know the angle must be 2700, right? And going back to this problem, there's 3 answer choices with 2700. And what we need to figure out next is whether the polygon is regular or not. But the thing is about this problem, we only know the interior angles. We don't know anything about the sides. And some of you might automatically think that just because a polygon has equal interior angles, that it must be regular. But that's not the case, because in order to be regular, you must have congruent sides. And we don't know if this has congruent sides. And just to give you an example, think of a hexagon, right? If you have a regular hexagon, pretend this is regular, you could just stretch it out. So if you stretch it out, um, and by stretch it out, I just mean lengthening these sides. You could lengthen these sides, but all the angles would remain the same measure. But obviously, these sides will now have will be longer, so this is no longer regular. So we don't know if this polygon is regular or not regular, so our answer must be E. Now, we're going to go over diagonals here, and a diagonal is just a line segment connecting vertices that are not adjacent. And by adjacent, well, adjacent basically means next to each other. So any two vertices that are not next to each other. So if you look at a square, you have two diagonals. And for the sake of time, I want you guys just to do the first one, and we're going to go over a generalization of this problem. So go ahead and try to do example 4.1. So I'm going to go ahead and start in example 4.1. So, since we haven't done any generalizations yet, we'll just bash it out for now. So you can draw that out this pentagon, and I mean, this one is regular, but our answer will hold for every single pentagon. So we just count out the diagonals in here. It creates a star, and a star has 5 sides, or you could just count it, and you see that the amount of diagonals is 5. If you did part B and you counted correctly, you'd get something like a shape like this, and you'll find that you have 9 diagonals. And this stuff, like, if we keep on drawing this stuff, we're never going to finish any of these problems, right? So I want you guys to go ahead and go ahead and actually go ahead and try example 4.2, and from here we basically solve the generalization. So go ahead and attempt 4.2.
So please don't try to
go ahead and
manually
pull out.
count this. It's going to take you a
Smart.
pretty long time. Instead, try to find a faster way to do it.
Well, example 4.2, if you feel like you know how to do generalization, go ahead and make the generalization right away. But if you don't, go ahead and look at a specific example of a decagon or even a smaller example and see if you can create a generalization. Because really what we're doing is trying to create intuition behind the generalization. Okay, so I'm going to go over the specific example of the decagon, and from here it should be pretty clear from how we derive our general formula for the amount of diagonals in an n-gon. So, as I said before, it's hard to look at everything at once, so we should focus on a single vertex. So let's just focus on a single vertex A. So if you have a decagon, we know that you can't, if you pick a certain vertex, you cannot connect to 3 vertices. And the 3 vertices are itself, you can't connect to A, and you can't connect to the ones right next to it. So that would be B and J. So what this means is we have 7 choices for the other endpoint of the diagonal. So for every diagonal, we have 7 choices for the other choice of the diagonal. So if you start like vertex A, you have 7 choices. If you start vertex B, you have 7 other choices. And therefore, our answer is 10 times 7, 70. Or is it? We've done something wrong here. And I want one of you guys to point out what we did wrong. Because it is true that we have 7 choices for, it is true that there are 7 diagonals emanating from each vertex, but we did something wrong here with our counting. Does anyone know what it is?
We duplicated them.
We have like 2 minutes, so I'm going to go over this really quickly.
Duplicated the
If we cut out for no
number of
reason
diagonals.
because the timer ran out, but basically we counted every vertice twice in accident. So if you have a diagonal connecting vertice A and C, we would count it once through A and 1 time through C. Okay. So that means we double count every single diagonal. Therefore, we divide our answer by 2. So 70 divided by 2. Oh, it's not 70 factorial, by the way, just 70 exclamation. So our answer is 70 over 2, which is 35. And from here, I'll leave you guys. I think from this example, it should be quite clear of how we can use this approach to generalize, but I think we're about to cut out. So with that, I'm going to. Caleb, should we end the meeting here?
Yeah, we're gonna stop here and continue next week. Remember, we will be sending out this handout, so in case you want to review this lesson or you want to check out what's going to be coming next lesson.
Actually, let me go ahead and finish the let you guys have some intuition behind the n-gon. So I think we're gonna cut out in like 2 minutes. So I think I'm gonna have just enough time to finish this. So looking at an n-gon, right? Oh, and to Krishna, Cisco cuts out every 15 minutes, shorten it. So I'm gonna go over this. So if you look at an n-gon, you can use the same like concept.